here's something that doesn't quite add up. London sits at roughly the same latitude as Calgary in Canada, and Moscow is actually further south than most of the United Kingdom. And yet European winters, on average, feel nothing like their North American or Siberian counterparts sitting at that same distance from the equator. The reason has almost nothing to do with the sun overhead and almost everything to do with the ocean, thousands of kilometers away from wherever you happen to be standing. There is a slow, massive current running through the Atlantic that works like a conveyor belt for heat. Warm water travels north near the surface from the tropics, releases its heat into the atmosphere, cools, grows saltier and denser, sinks near Greenland and Iceland, then creeps back south along the ocean floor. Scientists call the whole loop the Atlantic Meridional Overturning Circulation, or AMOC for short, and it single-handedly moves roughly as much heat northward as 1 million power plants running non-stop. That is part of why Western Europe stays several degrees warmer than its latitude alone would ever explain. People have known about part of this system for centuries without grasping the full picture. Benjamin Franklin helped chart the Gulf Stream in the 1770. Annoyed that mail ships crossing from Britain kept losing 2 extra weeks because captains had no idea they were fighting a fast river of warm water in the middle of the open ocean. What Franklin mapped was only the warm, near-surface half of a much bigger loop. The sinking, cooling, slow return journey south wasn't properly understood until the 20th century. Once oceanographers realized the whole system behaves less like a simple river and more like one interconnected engine, powered by differences in heat and salt. And that engine has hiccuped before, dramatically, in the planet's relatively recent past. Around 12,800 years ago, as the last ice age was winding down and the world was warming up, temperatures across the northern hemisphere suddenly plunged back into ice age conditions within decades, not centuries. This abrupt cold snap is known as the Younger Dryas, and the leading explanation is that a massive pulse of fresh water from a glacial lake roughly the size of the Black Sea flooded into the North Atlantic and disrupted this same overturning circulation. Ice cores drilled out of Greenland reveal roughly 25 abrupt warming and cooling swings over the last ice age alone, many of them tied to changes in this exact same current. None of that is folklore. It is written directly into layers of ancient ice and ocean sediment, which is exactly why, when a Hollywood disaster film in 2004 depicted the AMOC collapsing and freezing New York City solid within days, actual climate scientists rolled their eyes at the timeline, while still agreeing the underlying physics wasn't pulled out of thin air. So here's a question worth sitting with for a second. If this current has flickered before, long before any industrial civilization existed to blame, is a full shutdown today something humans could still avoid? Or is it simply a matter of time either way? There is no single clean answer yet, which is part of what makes this such an active area of research. But a growing body of evidence shows the AMOC has been weakening in recent decades, and that alone raises the odds that today's warming could push it toward a genuine tipping point, rather than just a temporary wobble. Climate scientists talk about tipping points constantly these days, and the AMOC usually sits near the top of that list, alongside the Greenland and West Antarctic ice sheets, coral reefs, and parts of the Amazon rainforest. A tipping point, in this context, means a system that can absorb a slow, steady push for a long time and then, past a certain threshold, flip into a completely different state relatively fast, and often struggle to flip back even if that original push eases off. For the AMOC specifically, the underlying mechanism has been understood in broad strokes since the early 1960s, when oceanographer Henry Stommel built a simplified mathematical model showing that ocean circulation driven by heat and salt could, in principle, settle into 2 different stable states. One state is the vigorous circulation the modern world currently relies on. The other is a much weaker, collapsed version. For decades, Stommel's model was treated as an elegant theoretical curiosity, not something anyone expected to matter within an actual human lifetime. What changed is direct measurement. Since 2004, an array of ocean sensors stretched across the Atlantic at 26 degrees north, nicknamed Rapid MOCA, has been continuously tracking the real strength of the AMOC. The first time humanity has had an ongoing pulse check on this system, instead of only indirect estimates. That direct record already shows real ups and downs, including a noticeable weakening between 2004 and 2012, before it partly recovered. Longer reconstructions, pieced together from clues like sea surface temperature patterns, suggest the AMOC has lost roughly 3 sverdrups of strength, about 3 million cubic meters of water per second, since 1950 alone. Some sediment and coral-based records go even further, hinting the current may now be at its weakest point in over 1,000 years. So the slowdown itself isn't really in dispute anymore. What has been much harder to pin down is the part everyone actually wants to know. How close is too close, and how would anyone even see a genuine collapse coming before it was already underway? That is precisely the gap a team of researchers at Utrecht University in the Netherlands set out to close. But before getting to what they found, it's worth understanding why this question is so hard to study in the first place. You cannot run a controlled experiment on an entire ocean. You cannot rewind the planet and try again. All scientists really have is indirect evidence from the deep past, real-world measurements barely 2 decades deep, and computer models attempting to simulate the physics of the whole climate system at once. Building a climate model realistic enough to even attempt an AMOC collapse is an enormous computational undertaking. These simulations divide the ocean and atmosphere into a 3-dimensional grid, calculating fluid motion, heat, salt, and ice at every point, for every simulated day, sometimes across thousands of simulated years in a row. That expense is a big part of why, until recently, nobody had actually managed to trigger a full AMOC collapse inside one of the complex, state-of-the-art climate models used in major international assessments. Simplified toy models, sure. The real thing, with all its messy feedbacks between ocean, atmosphere, and ice, not yet. So what would an actual collapse look like? Not inside a model, but for real. Picture Northern Europe's winters growing noticeably harsher within a single human generation, not over centuries. Picture farmers and fishing communities having to relearn, essentially from scratch, what kind of weather to expect year after year. Picture the seasonal rhythms that entire ecosystems, from migratory birds to fish stocks, have built their lives around, no longer lining up the way they always have. It wouldn't stop at Europe either. Heat that a weakened AMOC no longer carries north has to go somewhere, and models consistently show it piling up in the southern hemisphere instead, alongside shifts in tropical rainfall belts that billions of people depend on for their crops. So after building one of the most ambitious and expensive climate simulations ever attempted specifically to answer this question, what did the team at Utrecht actually find when they finally pushed a full complexity climate model past its limit? Using a detailed simulation called the Community Earth System Model, the same family of model used in major international climate assessments, the researchers ran a simulation stretching more than 2,200 simulated years. Starting from a stable, realistic pre-industrial climate, they slowly added extra fresh water into the North Atlantic, mimicking the combined effect of melting ice and heavier rainfall, an extremely gradual push, growing by less than 1,000th of a sverdrup every single simulated year. For the first 13 centuries of that simulation, the AMOC just wobbled along, weakening slightly but nothing dramatic. Then, within roughly 100 simulated years, everything changed. Its strength collapsed from about 10 sverdrups down to nearly 0. This was the first time researchers had ever triggered a genuine tipping event, not just a gradual decline, inside a full complexity global climate model. The knock-on effects inside the simulation were severe and fast. Northern Europe cooled by more than 1 degree Celsius per decade in the worst-hit regions. In the Norwegian city of Bergen specifically, February temperatures dropped by roughly 3.5 degrees per decade, a pace no modern infrastructure, agriculture, or energy grid is built to absorb gracefully. Parts of the Atlantic coastline saw sea levels rise by more than 70 centimeters as ocean currents reorganized themselves, and the Amazon rainforest's wet and dry seasons flipped entirely, putting its whole ecosystem under real strain. But the real headline of this study was never simply, yes, this can happen. Researchers already suspected that much. The genuine breakthrough was figuring out how to see it coming with enough warning to actually matter. Earlier attempts to build an early warning system leaned on statistical patterns, things like rising variability or growing autocorrelation in sea surface temperature data. The Utrecht team tested that same classical approach against their own simulated collapse and found it gave inconsistent, sometimes contradictory answers depending on exactly which stretch of time got analyzed. So instead, they zeroed in on something more directly physical, the flow of fresh water carried by the AMOC itself, measured far south near the tip of Africa at 34 degrees south. As the current weakens, this value dips to a minimum right before the whole system loses its balance, roughly 25 years inside the simulation, before the full collapse actually arrived. 25 years might not sound like much on a planetary timescale, but it is an enormous head start compared to a warning system that only tells you a collapse is happening as it happens. And this indicator isn't locked inside the simulation. It's something researchers can genuinely measure in the real ocean today, using existing monitoring networks, including one positioned at that exact same 34 degrees south line since 2009. When the team applied their method to 4 decades of real-world reanalysis data, they found the same telltale trend the model had shown right before its own collapse: a steady, measurable weakening of that freshwater transport. That does not mean a real collapse is booked in for a specific date. The simulation needed a genuinely enormous amount of added fresh water, something like 80 times the current melt rate of the entire Greenland ice sheet, to actually trigger its tipping point, partly because of known quirks in how the model distributes rainfall and salinity across the globe. The researchers themselves are upfront that real-world observation records, at most about a century long, still are not long enough to say exactly how many years might be left. What the study does establish is something researchers had long suspected, but never actually managed to demonstrate this cleanly. A full AMOC collapse is physically possible within the most realistic climate models available, not just inside simplified textbook versions. And there is now a concrete, trackable warning sign scientists can watch for, instead of having to guess. The study, led by René van Westen, Michael Kliphuis, and Henk Dijkstra at Utrecht University, was published in 2024 in the journal Science Advances. If you want to dig into the methodology yourself, the paper and our full write-up are linked in the description below.